Vabbè, in the meantime, keep clicking on, there is like after this, there is like the definition of the, let me see. So after the stress energy tensor, there is basically the contraction because we have written at the end G mu nu like this. So we need to write 8 pi T mu nu like this. So the command that you find in your notebook, the weird T that I defined in the notebook is basically just the contraction of the metric. So you see that there are like two stress energy tensor defined, a T and a weird T label, and the second weird T is just the contraction of the stress energy tensor with the metric to get the mixed components. You get it? And then you see it's not used, I mean, we will not use it, but there is this delta T, which is the covariant derivative of the stress energy tensor. I don't know how much it will take. It will take probably a while, well, depending on your laptop, maybe not, but basically that thing there computes explicitly this. Vado a prendere il cellulare, non vedo altra soluzione. No, pure dentro Costantino mi ha detto che non è tutto morto là. Mi dispiace che... Sì, sì, no, lui si è collegato adesso, si sta collegando. Ok, we're back. Okay, we were here. So as we were saying, this was the TTT, the time component of the stress energy tensor. As you see, basically depends on the energy density that I call rho plus the perturbation. Okay, before I was talking about this thing, this curly T, which is just a mixed components, because as I was telling you, we are solving those equations there in mixed forms. Those going to be slightly simpler. And then this is not used. I put it there just for you to see that this would correspond. It's a 4 vector, and because it's basically this. Okay, so it's the covariant derivative of the stress energy tensor. So it has just 4 indices on nu here. And you see basically contains the simple derivative of the stress energy tensor T. So the derivative, this D, is the mathematical operator that does derivative with respect to something. And in my case, it's the derivative with respect to the coordinates. So y are just t, r, theta, and phi. And then there are all these other terms. So the first line and the second lines, which are the contraction of the Christoffel symbols for the covariant derivative. Okay, now you can, in Mathematica, you can export things because I don't want, for example, to redo everything, the calculation from scratch. So this, in principle, you can export your quantities and then you can import so that you can work directly on the perturbed things instead of redoing all the calculations. At the end, what I define is the full set of field equation with that I call curly E, because what at the end of the story, what I am trying to solve is this, which basically means G mu nu minus 8 pi T mu nu equal to 0. Okay? Okay, let's go to compute and to isolate all the components first at the background level. So I'm taking for what I need are, and we saw actually yesterday, this is basically, this part recomputes the metric functions that we need at the background level. So basically gives you back the T of V equation. So the Tolman-Oppenheimer-Volkov equation. So we need the T component and the R component of that equation at the background. So this would be the TT component, and this would be the RR component. And what I want to find is an expression, differential equation for the two matrix function. And in particular, I want to take like the TTT, which depends only on B and the density. And I want to solve this equation for B prime. Okay, so this equation, if I click, this would be basically equivalent, this thing, to be B prime equal to this. Okay, this is exactly one of the equation that we have seen before. We have seen yesterday. Actually, this will give you the mass equation in 10 seconds. Then I'll take the GRR component of the fields equation, and this GRR depends on B, but there is like an A prime derivative. And so I basically want to get an equation that I call with domain, this is dA equal to this. So I'm basically solving the GRR components of the field equation for A prime. So this thing would be like this. A prime equal to this. And the same for, okay. So these are the two equations that we need to solve numerically. Then, actually we need it. As we actually said yesterday, if you remember yesterday, basically we had I cancel. We took one of the equations that we need to solve the T of V equation, to get the final form of the T of V equation from the nu equal R component of the covariant derivative of the stress energy tensor. This is what we saw yesterday in the lecture, and this is exactly this. So dt was the covariant derivative, which indeed we needed, and dt2, the second component, is just the radial part of the covariant derivative of the stress energy tensor there. So, and at the background level, basically this is it, the equation. And as we saw yesterday at the blackboard, this equation gives us a relation between the pressure and the derivative of the pressure and the derivative of the metric tensor, of the metric component A. Okay, so again, I can solve for this and get that dp, so p prime is equal to this thing here on the right hand side. So at this moment, we have this set of equations, A prime, B prime, and P prime, which are given by these things here. If you want to put all your equation in a more canonical form, what you can do is, instead, you can take your equation for this, your equation for what is the GRR, and we said yesterday that in the GTT, in GRR, so the GRR component for us is this, we were making like a sort of, we're actually introducing a function which is M of R, such that B of R can be written as 1 minus 2 M over R divided by R. And this gives a particular simple form for the Fields equation and for the ODE for B, which is very, very similar to the Newtonian case. And here in Mathematica, what this thing, you see, what this operation does I take dB, which is my equation for the B, so for B prime, and I replace B, dr, with this thing. So instead of this, basically this operation that is within curly brackets, replace every time that it sees B of R, puts instead these values, which is basically that thing there. And indeed, if you write this in this way, you get basically that instead of B, you have now everything expressed in M of R. And then you can basically, what I'm just doing here, very, very naively, is that I'm casting this equation in terms of, which is written as B prime equal to something, in a form which is M prime equal to something, which is this one, okay? So at the end of the story, the equation for B prime gives me the mass equation that we saw yesterday. So M prime equal to 4 pi rho square the energy density. All right, and I can do now I can just make a little simplification, and I can take my previous equation for P prime, and I can replace inside of here the equation for A prime, because remember that A prime is equal to this. So here, basically, what I'm doing is take the equation for the P prime, replace every time that I find the derivative of A, its values, and the same each time that I find B, just replace its representation in terms of M of R. So it would be this, and then you can simplify with Mathematica to get slightly easier form, and you get this. This is the second TOV equation that we saw yesterday. So yesterday, basically, we saw the two equations, the M over R equal to 4 pi rho R square, and then the P in dr equal to something, and that something is exactly this. So you recognize, for example, the two things that we discussed yesterday, that the total pressure in GR is given by the mass, but there is also an effective mass given by the pressure. We discussed this yesterday, okay? Now, just as a check, you can turn off the matter variables. So you can take, for example, dB, and you can tell Mathematica, put the density equal to 0 because I want to go in vacuum, and your equation will be this one. Now, if you solve this equation with Mathematica, and this is a differential equation, so basically, let me actually write in this way. So I'm basically here, what I'm doing is I'm solving the equation for B, putting the density equal to 0, equal to B prime, and I'm trying to find the solution. And the solution in Mathematica will be this. So when I solve B prime equal to its Einstein component term, I get this solution, okay? And then, so you get the solution for the GRR component, just depends on a constant that I can fix to minus 2m, and basically this gives me the Schwarzschild solution. So in vacuum, it should be, so for rho and epsilon and p goes to 0, the equation for B prime just gives me something with which depends on the constant, which is the total mass of the system, twice, and you get then the GRR as you would expect. You can do the same now in the A, in which what I do is I will have like A prime dr equal to dA, and then I replace, I put the pressure to 0, and instead of B, I put here the solution that would be the B of Schwarzschild. And then I would get a differential equation that I can solve for this. Now, if I solve, let me write this explicitly. If I solve this equation to find something like this, okay, and I can just, so basically my solution for A, which is the GTT, so what I'm finding is that the GTT is actually minus GTT, so A would be 1 minus 2m over R multiplied by a constant, which is C1 there, and I'm putting this constant to 1, which is basically means just reabsorbing, redefining the time variable. So basically, what I'm saying is that I have that my minus a dt squared in that case would be minus 1 minus 2m over r c dt squared. And I'm just defining a dt bar, which is square root of c dt, such that this would become minus 1 minus 2 m over r dt squared. This operation is just made here, setting the constant equal to 1. So in vacuum, basically everything will just reproduce Schwarzschild. Okay? All right. Of course, we don't have Schwarzschild. So for us, A and B will keep, will be just dummy function of R because they need to be integrated numerically. Okay, only in vacuum, outside the star, will have like the specific value. And let's go to the perturbative sector. So let's go at the linear order, and now we need to find, as we showed yesterday, we have like 4 components of the perturbation, so H0, H1, H2, and K, but at the end of the story, everything was coming to a single equation for H0. And this is because the Einstein equation will allow the simplification to express one variable in terms to the other. And I just want to show how this is done. So if I take, this is always like this. So if you want to solve up, find solution of Einstein equation, at the end of the story, you always end up in taking Einstein equation and combining them, massaging them. So finding the right way to use one component multiplied by a factor, sum to another component, such to simplify your fields equation in order to find the simplest form. And this is exactly what I'm doing here. Here, for example, I'm taking the theta theta minus the phi phi component of the perturbation. And if you do this, I'm basically taking epsilon theta theta minus epsilon phi phi equal to 0. This must be 0, these are my fields equation. And basically this part here is just a spherical harmonics, and then there is a part here which is the difference between the two metric perturbation. So the only way for which these things can always be 0 if this thing here is 0, which gives me a condition between the two metric perturbation. So basically, taking this combination of the fields equation tells me that H naught is equal to H2. Okay? So here what I'm doing is that I'm putting H naught, I'm doing this. I'm writing H2 equal to H0 equal of H. Okay? Then I take this is the R theta component of the fields equation. This depends on H prime and a kappa prime. Okay? I can always, it depends on of course, on the spherical harmonics, but this would be something like a function of R multiplied by the spherical harmonics equal to 0. Okay? So this equation here, and this has basically something with kappa prime plus something with H prime. Since this is equal to 0, this thing must be equal to 0, which basically gives me a relation between kappa prime and H prime. So I can express kappa prime, and this is what I'm doing, as a function of the rest. And you see now I have kappa prime as A prime, so this is the background, plus something which depends on the perturbation. So I'm reducing the system because now H2 is completely removed, and then I just have kappa prime expressed in terms of H prime. There is still the pressure that is going around. Okay, yeah, we need to remove it as well. And you can basically do this operation. So if you take the theta theta and the phi phi components, but instead of taking the difference as we did here, you sum up and you replace here the values that we found for kappa prime and its derivative. You find this nice expression which now relates delta p, so the perturbation, just as a function of the only metric perturbation which is left, and all the rest are just background variable. So taking another combination of the metric, of the fields equations, just allows you to express here the perturbation, what I call solve delta p. So basically solve such to cast the pressure perturbation as a function of background quantities and of the only perturbation left into the game. Okay, and now we need to basically make all the game in order to do the mapping, because remember that the final form of the log number is only obtained when you do all the mapping between solving the equation inside the star, matching the solution at the radius where it's vacuum, and then go to infinity. Okay, so the first thing that I want to do is simplify a bit the equations, okay, with replacing basically all the values that I found for the other metric perturbation. So here I take what's gonna be my master equation, which is ETT minus ERR, and I want to write this now, everything, as a function of H prime, and H dot dot prime. So I basically take this combination of the fields equation, and I replace all the values that I found for kappa prime, for the second derivative of kappa, and for delta p, such that now everything doesn't depend on any metric perturbation but H. So this is basically if you remember, yesterday we saw that the log number was basically defined in terms of a second order equation, which is this thing here you have in your notebook, okay? And that thing there is basically this thing here. So we have just replaced, or we have used Einstein equation to eliminate the perturbation time by time, such that everything now can be cast as a second order ODE, just depending, so an ordinary differential equation in the radial variables, and everything within the brackets is just function of the background quantities, which in principle you already know. So this, if you have clicked on the notebook, your EC will be your master equation for the H, for the metric perturbation that needs to be solved inside the star. And now we can do all the matching, okay? So to show how we do the matching, takes this equation, take EQ, so EQ is our final form of the equation, and as we said yesterday, we want to evaluate this equation at the border, where I told you that there is an analytic solution for this. And indeed, how do we see it? Take this equation and consider its vacuum limit, which basically means take the pressure, the density equal to 0, and the metric function to be coincident with their Schwarzschild value. So replace in the equation every time that you see the pressure or the density 0, and every time that you see A and B, put the Schwarzschild value. And you have this equation here. Okay? Now, mathematics is a bit stupid, so it has the function defined in a different way, but basically, in order to make it solvable in a fully analytic way, you just have to make a change of variable. So instead, this function depends on R. Now, I take this equation here, which is the vacuum limit of my perturbation equation, and I replace, instead of R, I put, instead of the radial function, I just introduce a new variable, which is this M1 plus X, doesn't really matter. So this equation that you see here is exactly the same as before, in which I made just that replacement. So I just changed the coordinate. And then this equation has an analytic solution. And indeed, Mathematica, you can solve it. Mathematica has this command, which is dissolve, which in principle tries to find an analytic solution to differential equation. It doesn't mean that it's always possible, but Mathematica tries to do it. So what I'm trying to do is try to solve this equation here and give a solution for H. I do it, okay. After I find the solution, I also go back to my original variable. So as I told you, in order to allow Mathematica to find the solution, I cast the equation for the perturbation in a nicer form, going from R to X. But then, since I want to go to my physical variable, I go back from X to R. And at the end of the story, I have this thing here, which is my analytic solution for H valid at radii larger than the radius of the star, where everything is vacuum. Okay? And that's it, because now I have this solution, and I have to match it far away, where this coincide with this is the GTT component of the metric tensor, which, as we've written last time, is basically an asymptotically flat space-time, which contains like 1 minus 1 plus 2m over r, and then there is the decaying solution, which is proportional to something that here it's q, so the quadruple, and then there is the r squared term, which is proportional to the tidal field amplitude. Okay? Okay, last thing that I forgot, the solution here depends, of course, on two integration constants. As we discussed yesterday, the solution here, the analytic solution, contains two constants that actually encode all the physics of the problem that then need to be matched with the GTT, the asymptotic form of GTT. Remember that the two constants of integration that were coming from solving that thing analytically were related, one to the quadruple moment and the other to the tidal tensor, and we need to solve them algebraically. So what I'm doing here is I'm constructing now so I have my solution for H0, or as I call it in the notebook, H for r larger equal than the radius of the star. I compute my G00, which is minus 1 plus 2m over r, plus h of r, which is this. Okay? Then I expand this thing for large values of r. So I have this would be like my GTT. Okay? But what I want to do is take the large r limit, because I want to match it for values of r much larger than the radius of the star. I want to match it with its asymptotically flat solution, which is given by the ACMC metric. And this is what I'm doing. So I'm taking the GTT, and when you do this command, which is series, means takes a Taylor expansion of the quantity inside series for large values of r at a certain order, the one that I need. Okay? And then if I do this, you see that basically there are the solution, and basically you have the solution now for the GTT expanded for large r that contains different terms. But I'm only interested in two terms. The one that goes like r squared, and the other one that goes as 1 over r cubic, because those are the terms that I want to match with the GTT written in the ACMC coordinate frame. And indeed, here I just want to, I recognize before I brought the notebook, that the C1 constant is related to the divergent part of the metric. So basically what I'm doing here is I am expanding the solution for large r, and then I'm taking just the coefficient of this expansion in powers of r, which is r squared. So this thing here basically means give me only the r squared. So this give me the coefficients in front of r squared. So the power of square power of r. And indeed it gives me 3c1 over m squared. And then I match it with the corresponding, the tidal amplitude, so the corresponding r square component of the ACMC metric. And let me cancel everything. At the end of the story, then this solves the two things. So I'm just equating the ACMC and the expanded form of my metric, and I just have an algebraic solution that I need to solve for the constant. So basically this thing tells me that at large r, the constant of integration is just proportional to the tidal field amplitude multiplied by m squared. And I can do the same for the decaying solution. So again, I construct the GTT, I expand for large r, and now I take the coefficient, which decays as 1 over r cubic, which is now this guy here, and I want to equate this with the terms in the ACMC metric which decays as 1 over RQ, which is proportional to the quadruple. I solve algebraically for it, and I get that the second integration constant is related to the quadruple moment. And that's it, because now what I want to do is take, this was my original equation for my original solution for H of R, okay, for radius for values of R larger than and equal than the radius of the star. And this solution here that was analytically is this, this guy here that you see on the last line, depends on the two integration constants, okay? So I can take this and the first derivative, which again will depend on something else, but is always proportional to this integration constant. And this is something that what I'm doing. So I'm taking the solution and its derivative, and what I'm doing is I'm replacing then the values of R with the values of, I want to compute that equation exactly at the radius. So I replace R, small r, with the radius of the neutron star, and instead of the two integration of constant, I just put the values of C1 and Psi2 that I found through the matching, okay? And indeed now, for example, this is the values, this equation U1 that you see there is just this, where instead of Psi1 and Psi2, I just put the two values of the constant that we found through the matching. This is evaluated at the radius. And also, I've replaced the quadruple with our adiabatic approximation. So with the condition that the tidal induced moments were linearly proportional to the source of the deformation through the tidal deformability. So you see that now lambda enters to the game. So now basically this equation 1 and equation 2, what just tells me that I have two equations which are fully fixed. So I basically have a function evaluated at the radius and its derivative, which are proportional to the tidal deformability, and then they depend on R and the mass of the star. And then that's it, because actually you can combine them, and so since they depend on these two things, you can actually solve them as a function of lambda, and you find that there is an analytic solution, as I showed you before, yesterday actually. So these two equations that are fully fixed can actually be solved together in order to eliminate lambda. And so indeed you find that lambda is then equal to this thing here. This was the expression that we saw yesterday. Is this. And the solution now depends on this thing that yesterday I called indeed y. And this y, so what I'm saying is just you can just basically use the two equations that we found. You can solve for the common factor that is inside them, which is lambda, just algebraically. And it gives something which is the tidal deformability as a function of the compactness, so just the ratio of the mass and the radius of the star, and on this quantity that I call y inside there, which is h, the derivative of the perturbation at the radius divided by h of r, is it? Yes, multiplied by r probably, something like this, yeah. So the only thing that you need to do now is, so that's all, because now you have the tidal deformability or the log number, because remember that this is 2/3 K2 R25. This comes from the background. And then so you have the log number, which is defined by this function here. Everything is known, is algebraically known. The only thing is that you need to compute this. And this comes from the numerical integration. So what you have to do is then integrate your perturbation from the center of the star, evaluate the values of the perturbation at the radius, evaluate the derivative of the perturbation of the radius, plug in there, and then you get the tidal deformability. Okay? This is it. Question? I mean, this is just a sketch, but question on this? Okay, if you want now, I can show you how we can actually solve for the stellar configuration, and basically, this is what the notebook does, compute this thing. So basically, this is the usual mass radius diagram that I show you at the first lecture. So each of these curves gives different stellar configurations for different equation of states. And in particular, like the red one is just a polytropic equation of state, so something which relates the energy and the pressure in this way with the kappa and gamma chosen like with these particular values. Gamma equal to is more or less something which is approximate, not too bad, neutron stars. And then the other one, so APR, GNH3, and SLI4 are realistic equation of state, which basically means tabulated equation of state. So for example, in the Git repository that you find, there is a collection of equation of state. So there is a folder with some data file, and here I just uploaded 3 of them. And these data files are like this. So they have different columns, there is a README file, but besides the first one, this is, for example, the pressure, the energy, and I guess the enthalpy, whatever it is. I mean, you just need, for this game, 2 of them, which are the pressure and the energy. These tables comes because, I mean, there is a nuclear physicist that has actually solved, for example, a many body problem at so has basically constructed So I would say that for the equation of state of neutron star, there are 2 classes which are like what I call the realistic, and then these are like the polytropic or analytic. So the analytic one or the polytropic one are those that relates the pressure and the density in a like sort of closed form, which is basically fully analytical. And then instead there are the realistic equation of state in which P as a P of epsilon comes from microphysical calculations. For example, like I want to understand how the pressure and the energy density relate in a system of interacting nucleons. So to do this, I have to solve a many body problem, for example, in which I have like a collection of particles with like kinetic plus like interaction potential, and I basically solve these at the microphysical level, and then I compute the resulting pressure and the energy density. So you don't have everything in a closed form, but you will get a table like that. Okay. All right, and so do you have this file? Is it working? Not working? Not at all? You have to download all the files. Otherwise, you have to, because there is a, so you can actually do, you don't need, I would suggest to restart the notebook because you don't need all the other things that we did. These are 2 separate parts. So you can basically do this. If you go on top of the notebook, there is a comma which is called exit, which restarts everything, and just then reload the path. Colors really doesn't. You don't need anything else but Stellar, which is a package that I wrote, and you can actually use it. So stellar.m is basically a mathematical package with different routines and functions, which, for example, solve numerically the T of the equation, so compute the background and then the perturbations. Jesus, I hate, it doesn't allow me to. Can I share multiple files? It's terrible. So stellar.m is this. Is it working? It's working now. Okay. So the T of V, let me work on this file. I'm sorry that I cannot I cannot share multiple windows. So Zoom allows me to show only one window each time, which is very, very pissing off. So this stellar.m is a package that does many things, including it has this T of V function, which is a pretty long function. Not too long, but basically it does several things, including, and I just want to go through, so you can just click on it. Just basically solve the background equations for the stellar perturbation, so gives you the star, and then solves for the perturbation. Okay? So it takes an input, the equation of state, the initial pressure of the star, and then like some other, this poly is a flag, so for example, if you take it false, you basically works as a, it takes as an input a realistic equation of state. If it works as true, it takes as an input a polytropic equation of state, and then so you need to specify the polytropic index k and the polytropic exponent 2. But okay, let's work with the realistic equation of state. So this basically does this thing here, so solves the this in principle solves these and these plus all the other equations, but it does in a bit of a smarter way that is more useful for the integration. First of all, what does it do? Yes. So the second equation is really like this thing here. Okay. The only thing is that instead of integrating over like the pressure, instead of using the pressure, I'm using the logarithm of the pressure, just because from a numerical standpoint, since I'm working with things which are 10 to minus 9, 10 to minus 10, or like larger or small, very small number, it's better to work with the logarithm. And the second thing is that when you're playing this problem, so I want to construct the star, I actually don't know where the radius is. So if I integrate this thing, okay, when do I stop? Because this is basically integration from the center to something. The problem is that I don't know where this something is. In principle, you can use what in numerical methods is basically a shooting. So I can actually try to compute, to integrate this thing up to certain values of R. Let's call it R, capital R1. And then I compute the pressure, and I see that the pressure at this point is, for example, 10 to minus 5, the central pressure. Remember that I'm actually, the radius for me is something for which the pressure is 0. Now, you're never going to find 0. This is a numerical problem. So the only thing that you can really set is saying, I'm looking to a values of P of R, which is x times smaller than the center of the pressure at the center. Okay, this for me will be my 0. You're never going to find exactly 0. Okay. The problem is when do you stop in order that this condition is satisfied? So you can do like this. You can do multiple tries. So I go here and I say, this is 10 times smaller. I want it like 20 times, 100 times. So I increase slowly R. Or you can do something a bit smarter. I can reverse this equation. So instead of solving P dp in dr, I can actually solve dr in dp. And then at this point, I integrate, instead of as a function of R, I integrate as a function of the pressure between P0, and then the radius of the star just basically becomes an extreme of integration. So you see, this, I need to integrate this between, let me put this in a more clear way. This thing here gets integrated between R0, so the center of the star, and capital R, which I don't know where it is, because my condition is not on capital R, but it's on P of R that must be, let's say, 10 to minus 12 P0, which is my 0. Okay? So this equation, if I want to solve this equation, I have to run to this process. And I have to try different values of extreme of integration until I get that is at least 10 to minus 12 my central pressure. But I can do something smarter, which is integrate like this. And then at this point, the integration is completely known because I decide from the beginning which are the extreme of integration, because this thing here is not integrated in the R domain, but it is integrated in the P domain. So it starts from P0, and it ends at a value that I decide is my 0, which is in this case 10 to minus 12, the central pressure of the star. P0 is this. P0 is up to you. Because basically for an equation of state, for a realistic equation of state, there is only one parameter that determines all the solution of the problem, which is the central pressure. So that's basically, it depends. So each value of P0 that you take as an input will correspond to a different star that goes on top of this line. So different value will correspond to different neutron star. It's a free parameter in this. Okay? And this is what I'm doing here. So if in that you see here in the notebook, there is not dm over r, but I've solved everything in terms of the pressure. So I basically wrote all equations like this. The m in the p, which it's the m in the r in the p. So instead of integrating in the r, I'm actually integrating with respect to the pressure, but the two are very, very easily related. Okay, the integration with respect to the pressure is just given by, this is the usual 4 pi epsilon rho squared, and then I have dr in dp, which is the inverse of the second t of the equation. So you see, and indeed, this term here is the usual T of V component for the mass multiplied by R prime, which is this thing here. And this is basically this guy here. This looks a very complex thing, but it's nothing more that R prime on the first line, that the inverse of the second T of V equation that we have shown yesterday. Because instead of computing dp in dr, I'm solving for dr in dp. Just a smart way to integrate stellar equations. Okay, and that's it. This basically solves for the background. Here it's a very general integrator. So together with the mass and the pressure, the radius, there is also the nu. So basically, yesterday we wrote the GTT as E2 nu of R. So this also gives a solution for nu of R. And so this basically solves completely the background, because then the M goes into the GRR component. So that block of the function gives GRR as this, because it computes M of R, and then computes nu of R, and so also the GTT is fully specified, and that's it. And then from when you solve from these, you basically get the values of the mass and the radius of the neutron star as the values of m of r and of the radial function at the border. This x2 is defined at the beginning, and is this. So basically at the beginning I define two quantities which are my extreme of integration, which is x1 is the logarithm of p0, so it's basically the center of the star, so this is x1. I told you that I'm integrating everything in the pressure and in the logarithmic form. And then x2 is the logarithm of 10 to minus 12 p0. This 10 to minus 12 p0 is for me 0, basically. Is the vacuum of my external configuration, and is this one. Okay? So when I compute m of r, nu of r, and the radial profile, for example, the total mass will just be m evaluated at the boundary. And this is it. Where is it? This is, I lost it. Okay, and the last thing is that is this part here, which is the integration of the perturbation. So this is the integration of the H, which is the metric perturbation. It comes exactly with the same structure as before. You have to specify the initial condition that we discussed yesterday. So in this code that you can play, there are initial conditions for all the variables, and in particular, there is a condition for H, which we discussed yesterday. So we saw that in order to integrate the equation for H second plus H prime plus H, you need to study the values of the function that as R goes to 0, and we saw that this was something that was a constant times R squared, and that this constant was irrelevant to the problem. We saw this yesterday, and this is exactly what it's here. So this is the initial condition for the perturbation H, and this is the initial condition for the first derivative of H. Since it's a second order equation, we need two starting conditions, and this is the second derivative, the first derivative. Just to tell you that when you solve like for the log number, it's easier to cast the system. So instead of the second order system of equation, it's easier to work in a system of linear order equation. And you can always do this because basically I define a beta, which is the first derivative, and then this equation, which is second order in H, becomes first order in beta. Okay? And so I get this. This is basically, these two equations here are equivalent to this. It's just that this is second order and this is a system of two first order, which is slightly simpler to solve for Mathematica. And I would say that's it. Okay, nothing. This solves completely all the equations. I mean, you get then the values of H and of its derivative. Again, we need basically, this is the final expression of the log number that we have seen several times. And this log numbers depends on the compactness of the star, which is the radius, the ratio between the masses and the radius. And it also depends on the values that we have written at the blackboard and on the slides. It also depends on the value of the perturbation at the boundary, and this is exactly this W, which is the Y at the blackboard, which is basically beta, which is the H prime in this system of ODE, evaluated at the boundary, so at the radius, multiplied by R, the radius, and divided by the values of the perturbation H at the boundary in R. Okay? You plug this in your analytic expression for the log number, and then you can get the log number and the tidal deformability. And I think you should try to click it now. If you now just run these, So you click on Stellar, which basically means that you load the package, then you upload the different equation states. There are many, and does it work? No. Yeah, okay. Yes, the table, but I mean, you can just compute like these things here are for standalone values. So it gives you the mass in solar masses, the radius, the compactness of these. This is the log number, and then this the tidal deformability. I told you the tidal deformability is a very big number. Here is of the order of 10 to 4. And if you then so this function, which is solves again the background and the perturbation, at the end for a given equation of state just depends on the input, an input parameter, which is the central pressure of the star. So if you vary the central pressure, so I'm taking different values here, and I make a table with different values of central pressure, then you can basically draw these lines, which are like the masses, and this is compactness, still background quantities, at the end the log numbers. Okay, for the various things. Okay, I think I won't do anything else because probably it's already enough, and we haven't done the break, but do you have questions in general again on all these things and on
So basically what we do is first solve the background, then we do the perturbation of the field, and then we solve this in the star, then outside the star, and then match this to the faraway radius, right?
yeah, exactly.
And then with that we can relate the
Exactly, when, exactly.
to the other and get the log number.
Yes. There is a, yeah, sure. Yeah. Not that particular equation, but if you massage that equation, you get exactly the Reggio wheel. Not the Reggio wheel, the Zerilli. Indeed, you just read my mind. There is probably a last thing that I can show, is that, so look at this thing here. This was like our analytic solution for, so this was H for R larger than the neutron star radius, so in vacuum in principle, or in vacuum. And it depends on some of these things, blah, blah, blah. And we related the two constants with the quadrupole and the tidal field. In particular, C2 is the constant related to the quadrupole. Okay, so C2 is the constant that is related to the induced moment of the neutron star that is deformed by the tidal field. Now forget about the neutron star, and instead of neutron star, assume that all of this is perturbation on top of a black hole. It would be, the procedure would be just exactly the same, it's just that you would immediately have this equation, because your A and B, your metric solution, would immediately be the Schwarzschild background. This equation here has a very, very bad behavior at the horizon of the black hole, because if you plug R equal to M, there is a logarithm that makes that perturbation to be divergent. So since I want my metric to be regular, there is only one way that I can cure this divergence, is that since this C1 and C2 are constant of integration that are fixed by the physics of the problem, so it needs to be specified by me or the particular problem, the only way that I can cure this divergence is fixing that psi2 such that it kills that divergent part. So I need to put C2 equal to 0, because C2 is also in front of everything. So basically, for a black hole, I need to put that constant equal to 0, but that constant is related to the quadrupole. which basically means that the induced deformation will be 0. So for a black hole, the log number is 0 because if I compute perturbation, they will be divergent at the horizon. And since I don't want, practically speaking, this divergence, I'm forced to put one of those constants to 0, and I actually forced to put to 0 exactly the constant that gives me the quadruple. Basically the log number, because the quadruple is lambda e. And so this is why yesterday in one of the last slides we saw that the log number or the tidal deformability for a black hole is 0. Because if you compute everything, at some point you're going to end up in an equation that is divergent at the horizon and then creates problem. Of course, like for a neutron star, R is always larger than 2m, so that will have like a finite value. Yeah. It would work, and indeed, when I said briefly that a boson star don't have like compact object like boson star are not that compact as black hole, so they are always radii larger than 2m. You will have like mimickers which have like 2m 1 plus delta, and you will find indeed that the log number would scale as log delta. And this is exactly because the 2m would go there, and so you will have a logarithmic term there. And this is why I told you, if you remember the plot, I told you, even if the deformation is very small at the level of Planckian level, the log number is not dramatically small because it has a logarithmic dependence on the shift, and because it's that. For a black hole, you just get immediately that equation because everything collapses to vacuum. And if you replace the values of the would-be horizon at 1 plus delta, you get that dependence. The equation of states that some of these are actually compatible with the observations. If you actually, some of the names that you're going to find in the folder are exactly these. So yeah, APR, which is one of the equations that is right at the beginning of your notebook, is just this one. Okay, so in the ballpark of equation that I gave you are like, there are some models that are compatible with the observation and some of them which have been excluded by this. It's actually I don't want to say a weird game, but the observation of neutron star done by LAGO and Virgo and by other probes, for example, by millisecond pulsars, by NICE, are a bit in tension in the sense that the one binary neutron star that we observe with LIGO and Virgo seems to suggest the equation of state are very compact, produce very compact stars, while the stars that we observe with electromagnetic signals, for example, like the NICER observation, provides like hints on stiffer equation of state, so equations which are a bit fluffier, so less compact than these things here observed. Other questions? Curiosities? No?
Usually in a more complicated kind of thing that is rotating with basically we saw that the quadruple is going to be related to the R squared term, and then there's another R over
Cubic.
to the minus, right? Is that going to happen all the time, or it becomes more complicated?
No, it will happen. It's just that it's more complicated to define something that is uniquely, is not easy then to identify the one over, uniquely the 1 over R cubic and in the other piece that you expand. So you need to make an analytic continuation and blah, blah, blah. But the rule of the game is always that one.
So here, maybe like this perturbance, like the only like how many times it is only linear terms.
Yeah.
Will it affect this
Yeah, yeah. Oh, you can compute other second order perturbation which are incredibly more common.
First, in the start, we like took linear term of G, and then second time, we will try to
No,
calculate
sorry.
R,
Yes. Say it again.
So here, when we try to solve this equation,
Yeah.
we always like take the leading
Yeah, yeah,
terms.
yeah, yeah.
So how much this may affect to the solution.
No, this is just a full. I'm doing this step by step to just you can do everything and just linearize at the end. It's just that this is simple.
That it won't affect.
No, absolutely. It's just for commodity.
You will also upload the notes of the
I'll upload the PDF. Yeah, I can upload like the end written notes if you.
Yeah, we need notes also.
Okay. Yeah, sure. Okay. Have a good lunch.